You ever think about taking a vacation in orbit? Sounds ridiculous, right? Well, when the Space Needle here in Seattle was built in 1962, back at the dawn of the space age, lots of people thought they would soon be taking trips just like that. Of course, it hasn't quite worked out that way. It cost about $500 million just to take the space shuttle out for a spin. Kind of an expensive vacation, isn't it? One, please. Thank you. But what if there was another way to get to space? And what if that way were as easy and as cheap as riding an elevator? Well, strange as it sounds, some people think this kind of trip might just be possible one day, thanks to something known as the space elevator. A 22,000-mile long cable that we could ride straight to outer space.
What we're talking about is building the biggest thing ever.
And what enables this big idea is the discovery of something so small you can't even see it with the naked eye. A new material called a carbon nanotube. Fueled by the promise of these tiny tubes, people are already working to turn the space elevator into a reality.
It's basically a fairly straightforward system once you get down to the nuts and bolts of it.
First, launch a satellite to geosynchronous orbit, 22,000 miles above Earth. Then, lower a cable or ribbon and attach it to a platform at sea. Clamped to the ribbon, elevator cars or climbers could carry people and payloads up and down. Lasers on the ground would beam energy wirelessly to solar cells on the underside of the climber, powering electric motors for the 22,000-mile journey. Okay, I know what you must be thinking. A 22,000-mile elevator ride? These people are nuts. Like, what would even hold it up? Well, the idea is not quite as crazy as it sounds.
Imagine I have a yo-yo in my hand. As you spin the yo-yo around, the body of the yo-yo is thrust outward, and the string connecting you to the yo-yo is held taut. Well, this is the same principle that would keep the space elevator up. We're basically making a planet-sized yo-yo.
A space elevator could be safer and cheaper than rockets, giving routine access to the solar system. Bringing this far-out idea down to Earth, NASA recently funded a competition in New Mexico to build and race space elevator prototypes. It was held at the X Prize Cup, a carnival of cutting-edge space technology. In the tradition of competitions that stretch farther back than Charles Lindbergh's transatlantic flight, the aim is to inspire new advances in technology.
Wow!
This year, teams of students and weekend inventors are vying for the $150,000 in prizes in the space elevator contest.
I heard about this competition and I thought, wow, you don't have to have $1 billion in an aerospace company to do this.
We're definitely at the cutting edge. You're going to see stuff go wrong today.
The racetrack is a 50-meter ribbon suspended from a crane. Teams had to design and build climbers, then race them to the top of the ribbon. In place of the laser that might otherwise power a real space elevator, they could use only energy from the sun or beam from the ground. The best time wins, as long as you go faster than a meter per second. One of the first to try their luck is a high school team from Germany, with an elevator sporting an intimidating solar panel and name.
Turbo crawler.
Turbo crawler?
Yeah.
All right, that sounds mean. Sounds like it's gonna win.
Yes.
But as Turbo Crawler is about to take off, the wind picks up. Turbo Crawler gets out of hand, and the Germans are grounded, at least for the time being. Julie Belrose and her team from the University of Michigan are next to jump on the ribbon.
The whole big idea behind doing this is to get engineers in school to start working on this. At the end of this event, there are kids here who are going to know more about space elevator technology than NASA scientists are.
Julie's climber is powered by a dozen spotlights that each have to track the solar panels all the way up the ribbon.
Get on, man up!
The climber gets off to a good start. But the higher it rises, the harder it becomes to hit the solar panels with the spotlights to keep it going. After about 6 minutes of stopping and starting, the climber reaches the top.
We didn't make it in the time required, but one of the goals is to make it to the top, so we're very happy.
NASA's prize money is safe, at least until the contest resumes the next day. Now, if you think the whole idea of an elevator to space sounds like science fiction, you're right. It was popularized in the late 1970s in a sci-fi novel called The Fountains of Paradise by Arthur C. Clarke.
At last, we can build the space elevator, and then we will have a stairway to heaven, a bridge to the stars.
But as long as people have dreamed of building that bridge to the stars, no material existed to make a cable that's strong enough. That is, until we found that one of nature's most common atoms, carbon, was leading a secret life.
I wouldn't say carbon is promiscuous. I would just say it's very open-minded.
Carbon atoms just love to form extremely strong chemical bonds with one another. We knew they could be arranged in a lattice to form diamond, or in sheets to form graphite. But until recently, we had no idea they could also form tiny spheres called buckyballs, and tiny tubes called carbon nanotubes. Much stronger and lighter than steel, and able to conduct electricity, these cylinders of pure carbon have been called a wonder material, a new building block that might be used in everything from electronics to airplanes. But as a space elevator cable, carbon nanotubes have some big problems. The longest ones ever made are only a few centimeters, and joining them together end to end, one at a time, is simply not practical. So how would we ever use these tiny tubes to make a cable that's 22,000 miles long? Deep in the heart of Texas, scientists are taking a different approach to assembling carbon nanotubes.
It's the dream of the future, but it's an achievable dream.
To make a batch of carbon nanotubes, bake a silicon plate coated with iron particles at 1,300 degrees Fahrenheit in a special oven. Then add a dash of acetylene, a gas that contains carbon. When acetylene comes in contact with the iron, it releases its carbon atoms, which assemble, as seen here, into nanotubes. When the plate comes out, it's coated with a black soot that contains trillions of carbon nanotubes, all aligned vertically in what Ray Bachman calls a forest.
Think of a bamboo forest.
But unlike a real bamboo forest, the trees in a nanotube forest tend to stick together, thanks to a faint force operating at the nanoscale, called the van der Waals force. It's sort of like magnetism.
So when you pull one nanotube out, you pull its neighbors, and then they pull out their neighbors.
Pulling a whole row of nanotubes from the forest on the left, they can draw out a ribbon of pure carbon nanotubes, held together by nothing but the van der Waals force. This ribbon is less than 1,000th the thickness of a human hair, and it's stronger than steel. But can nanotube ribbons ever be made strong enough for a space elevator cable?
That is an unresolved question. But in science and technology, I've learned to never use the word never.
Back in New Mexico, the mood is more optimistic as the second day of the space elevator competition gets underway. Among those hoping to claim NASA's $150,000 prize is Brian Turner, captain of a truly homegrown team, the Kansas City Space Pirates.
I've got my dad, my stepdad, my mom, my uncle, great-uncle Max.
Uncle Max, I'm Neil Tyson.
Neil.
All right, you're one of the family affair. If you win, that probably means more to you than just getting the money.
Oh yeah. I don't know. I think.
Hoping to make their elevator sail up the ribbon, the Space Pirates pull out their secret weapon, 15 mirrors, each the size of a twin bed.
One person in each mirror.
Beaming sunlight to your collecting mirror,
right,
to the solar panels,
right,
giving the energy to climb.
Right. Are you ready? All right, here we go.
Halfway up the ribbon, the wind kicks in again.
Gotta get up there. I'm gonna go look at it this way.
Bouncing in the breeze, the parabolic mirror can't stay focused on the solar cells.
Come on.
And the Pirates' elevator grinds to a halt.
Come on. If the wind hadn't been bucking, I might have been better off. But I can't believe I didn't make it to the top. I figured I could fight my way up there.
Next up, and favored to win, is the University of Saskatchewan Space Design Team, or USST for short.
Go time, right? It's go time.
Their secret weapon, a stationary mirror to reflect a spotlight straight up the ribbon to the solar array.
Go back a little bit. Okay, back to
phase one.
It looks like they'd make it to the top in record time, fast enough to claim the $150,000 prize. So did they win?
We have to have a little discussion about that.
Before the prize money can be awarded, the remaining teams get one last chance. The German turbo crawler crawls all the way to the top, but it's no prize winner. And late in the day, a team of high school students from California posts an impressive 2-minute run.
Pretty good that we got 2:02.
It's going on our resumes.
Yeah.
But in the end, the prize money went unclaimed because it turns out Saskatchewan fell just short of the minimum speed of 1 meter per second.
I mean, next year most of us are coming back, and we are going to just totally, take it up 2 notches and just go all out.
But will we ever take a ride in a real space elevator?
I think it's crazy, but I still think it's possible, and I think it's something that if we can do it, we should do it.
Well, one thing's for sure. We've got a long way to go before that happens. But who knows? Perhaps someday technology will catch up with our imaginations and take the space elevator out of the realm of science fiction once and for all.
Carbon nanotubes are a fantastic material. Light, strong, small, highly conductive and versatile, they're finding uses in everything from lightweight composites to high-performance batteries and touchscreens to drug delivery systems. But how safe are they? Research is increasingly showing that the wrong carbon nanotubes in the wrong place are potentially bad news for your health. The trouble is, this isn't much help without knowing what a wrong carbon nanotube looks like and what the wrong places are. The trouble is, carbon nanotubes are not just carbon nanotubes. They might be short, long, thin, fat, straight, curvy, tangled, spiderweb-like, bunched up in a tight ball, single-walled, multi-walled, big clumps, small clumps, or almost any combination of the above. And the risks they present depend critically on what type of carbon nanotube you're looking at. A very long, thin, straight, multi-walled carbon nanotube, for instance, is a completely different beast to a spiderweb-like cluster of single-walled carbon nanotubes. On top of this, chemistry matters. It's easy to think carbon nanotubes are just carbon, so what? But in addition to the supreme importance of how those carbon atoms are arranged in the material, carbon nanotubes often come with additional chemical passengers. These might be metal nanoparticles used in their production, or chemicals added to their surface to make them easier to work with, or even drug molecules inserted into their core to create more effective therapeutics. In all cases, the specific chemistry of a given carbon nanotube is rather important. Then there's the question of where the carbon nanotubes are used, and how they are used. It's easy to imagine how someone might breathe in carbon nanotubes while handling them as a powder. Harder if that powder has been suspended in a liquid or formed into hard pellets, though. And once the nanotubes have been used in a product like a battery electrode or a carbon composite bicycle frame, it's much more difficult to understand how a significant exposure might occur, especially as this material is often used in extremely small quantities. And because of their size, shape and chemistry, you need to work really hard at pulling carbon nanotubes out of a product once they're in it. And when you do, they don't often look the same as the material that went in, which means that research on the toxicity of freshly generated carbon nanotubes may not tell us what we need to know about the hazards of those that are released from products. The bottom line is that not all carbon nanotubes are created equal, and any residue of risk equity that might exist is further eroded by how they are used, which leaves us with a rather large challenge. As we learn more about what makes carbon nanotubes toxic, what do we need to do to understand more about who is likely to be exposed to what, and how exposures can be reduced to acceptably safe levels? Because without this, the responsible development and use of carbon nanotubes is going to be tricky, to say the least. For more information on carbon nanotubes, check out the links below, and stay safe.